Welcome to lesson 7 of our friendly introduction to abstract algebra. The headline for this section here is groups, groups, groups. Until now we do not really know very much examples of finite groups, and this is going to change in this chapter here. So we start by asking a very simple and natural question. If I have any fixed natural number, is there a group of this order, meaning a finite group with n elements? Well, for even numbers, we know there are the general dihedral groups. We studied them in one of the problem sets. They always have order 2n for the regular n-gon, so we know that there exist groups with even order. They are all non-abelian except for D2, the symmetry group of the straight line with two vertices. So the question would be, is there an abelian group of order 2n? Or for example, how about n equals 17? We do not know any example of a group of order 17. And this is all going to change now because we talk about the integers modulo n. First of all, let me give you a quick overview of this video. First, we will talk about the following equivalence relation on the integers. Two integers are said to be congruent mod n, any fixed natural number, if and only if n divides this difference b minus a. And I will remind you that you already showed that on a problem set. We will show that there are exactly n distinct equivalence classes, and as usual they partition the integers. And then we will make this very important definition. The factor set of the integers mod this equivalence relation is called z mod nz, consists of these elements. We will look at an example for n equals 5, and we will find out that one can actually add those equivalence classes and that there is an identity and that I have inverses, and then we will prove in general that this here is a group under the to be defined operation of addition, and it is clearly a group with n elements. And we will also show, which is quite trivial, that this is an abelian group. So we can answer this question: yes, there is a group of order n for every n, namely the integers modulo n. Oh, and if time permits, at the end of the videos we're going to look at some direct products of these groups. All right, let's look at the details. So we take two integers and define the congruence of those integers, mod n, a given natural number, a fixed natural number, as follows. If b minus a is an integer multiple of n, which means the same as n divides b minus a without remainder, of course, then we say these two integers are congruent mod n or modulo n. You might remember in the videos for the last lesson I told you please do this exercise, it's very important, and this is why. By exercise 1 on problem set 6 you should by now know that this here is nothing but what we called back then A equivalent B sub n here. This is the same definition, so this here is an equivalence relation on the integers. The equivalence classes look as follows. We wrote them with these brackets here in the last lesson. Those are all, or contain all the integers that are equivalent to a, meaning they are congruent to a mod n. And those can be written as a plus nz. This is an abbreviation for 0, n, 2n, 3n, minus n, minus 2n, and so on. So we add to a all these numbers and we end up with this equivalence class. Because this notation is a bit tedious to write down, we abbreviate it as follows: a bar. This line over the a is defined to be this equivalence class, and in this context we call it a congruence class or the residue class of a mod n. Okay, and also this proposition should seem familiar if you did this exercise last week. There are exactly n residue classes mod n, namely 0 bar, 1 bar, and so on up until n minus 1 bar. And z can be written, the integers can be written as the disjoint union of all these n different residue classes. So r runs from 0 to n minus 1. If I take the union of all these, I end up with all of the integers. Okay, so we start with any arbitrary integer. Let's call it a. Now, we haven't proven this, but let's take this as a granted fact about the integers from high school. You can divide two integers with remainder, meaning I can find for a and this given n an integer q such that a can be written as q times n. In general, there will be a remainder plus r, and I can do this so long until r is one of the numbers 0, 1, and so on up to n minus 1. So r is a positive integer that is less than n. But well, this means that a, which can be written like that, is congruent to r modulo n. Why? Because by definition, the difference of a in this form and r, where the r can be cancelled, is simply q times n, and this is obviously divisible by n. So that means here those are congruent mod n. That's a good rule to remember. If here is a multiple of n, you can just cancel it away if you use here the congruent sign, these three lines. But that means exactly that the equivalence classes of a and r are the same, because they are equivalent by definition here. And when they are congruent, by definition they are equivalent, so they generate the same equivalence class. And in the new notation here, this means that a bar equals r bar. And this proves there are exactly those different residue classes. And of course, those are really different. There are no two residue classes here that contain same elements. So this proves that there are actually these n different residue classes. And now we just cite proposition 6. All the equivalence classes taken together always form a partition of the set. And this means exactly that they are disjoint and that their union gives me the whole set, and that's it. So z can be divided into these residue classes here. So now we define the factor set of the integers modulo this equivalence relation of congruency or congruence as z mod nz, defined as this factor set, and as we have just seen, this factor set consists of n distinct equivalence classes. Now these are supposed to be friendly videos, so it's high time for an example. So let's take n is equal to 5. That's a good picture to keep in mind when working with these mod n things. You take the number line, here are the integers, and you roll this line up into a circle. That's the picture behind this. So what do? We take 0, and here we take the residue class of 0 as one new element. This is our factor set. So we start with the integers, and here we have the factor set z mod 5z, which can be visualized as this circle here. What does that mean? Which elements lie in the residue class of 0? The residue class of 0 is 0 plus 5z. So all the integer multiples of 5 added to 0. So I have 5, I would have 10, I have minus 5, and so on. So this here is minus 5, 0, 5, 10, and so on. Next, we take the number 1 and associate it with its residue class, 1 plus 5z. This contains the 6, it would contain the 11, and so on, and here the minus 4. Not going to write that down every time, you just look at that. Then we take the number 2 and project it to its equivalence class or residue class 2 plus 5z, which would contain 7 minus 3 and so on. So, and finally the residue class of 4, which contains 4 minus 1, here would be minus 2, then the 8 and so on. And then it's done because 5 lies in the same residue class as 0, so we repeat ourselves. So we get a watch with 5 dots, and we can actually calculate on this watch, as we will see. So to get used to this congruence notation, 11 is congruent to what? Mod 5. And we always want to find a number between 0 and 4. So I write 11 is what times 5? It is 2 times 5 plus 1. And this means that 1 is in the same equivalence class as 11. So 11 would be congruent to 1 mod 5. The same for minus 4. Minus 4 can be written as minus 1 times 5, which is minus 5, plus 1. So again, minus 4 is in the same equivalence class as 1, which we already know from here. So the equivalence class of 1 would be dot dot minus 4, 1, then 6, 11, and so on. And now, as always, with the factor sets, you think of all these numbers as being put into a bag, and on this bag I write 1 bar. And this here is the collection of 5 different bags containing all these numbers, but now they are our new elements that we are working with. This is important to understand about factor sets. So z mod 5z would be this set here. I have 5 different residue classes, and they are the elements of this factor set here. Now, as I've said before, you can actually calculate with these residue classes, and this is the important observation here. So we take 1 plus 4. Naively, I would end up with 5, so I go 1 further, and 5 is exactly the same as 0 mod 5. So let's try. Taking 1 plus 4, taking the numbers, adding them, and then taking the residue class. So this is the residue class of 5. But the residue class of 5 is just 0. So I end up with 0, which is in perfect agreement with this watch picture here, because 4 plus 1 gives me here this dot, the residue class of 0. And this is especially important. 1 bar is the same as minus 4 bar, because they lie in the same equivalence class, so they generate the same equivalence class. The same for 4 bar. 4 bar is the same as 9 bar. So I could as well write down this, and this here is the same expression as this, because the residue classes are the same. So I better end up with the same result. So let's see. Minus 4 plus 9. Oh, how nice. This indeed is 5 bar, which is the same as 0 bar. This is what we call being independent of a representative or well-defined. Because if this definition would depend on the choice of representative, there's no way I could make a well-defined definition out of it. The same with 2 plus 4. In this watch picture, if I go 2 further, I should end up with 1. Let's see. We end up with a residue class of 6, which is the same as the residue class of 1, because 6 is congruent 1 mod 5. All right. There is an identity obviously it's the residue class of 0, because if I add that, then for example here I would have 0 plus 4 is 0 plus 4, which just remains 4. And also I have inverses. What, for example, would be the inverse? Here we write it as minus the element, not to the power of -1, because we are in an additive group. And there we most often use this here. Minus 4 bar, this is just 1 bar. Why? Because 4 bar plus 1 bar, by this definition, gives me the neutral element, the identity 0. So, and likewise, all the other elements have an element which give 0 bar if I add them. So all the elements have inverses. And of course, this is associative because this addition here is associative. And this shows actually that this set here, together with this operation, is a group of order 5. So we have found a group of order 5. Of course, it's abelian because here we can change the order. So that's an example of a group of order 5. And in the second part of this video, or maybe I'll split it up in 2 parts, because it's already about 20 minutes long before cutting, we're going to prove that this is actually possible on Z mod NZ. So we use this idea here and generalize it and see that I always end up with a group with n elements. All right, see you soon or in the next video. All right, as announced right before or in the previous video, we are now generalizing the idea of Z mod 5Z to a general n. So as always, let n be a fixed natural number, and we abbreviate the factor set C mod NZ with Z sub n, or just C mod n or whatever. And now I define an addition. For now we write it as plus with the circle around. After this proof we're going to leave the circle away and simply write plus. So I take 2 elements, K bar and L bar, 2 residue classes mod n, and I define their sum to be simply K plus L and then residue class. Then I claim that this is a well-defined operation. I'm going to explain to you in a minute what that means. And that Zn, this factor set, together with this addition, is indeed a group of order n and actually an abelian group of order n. So we can answer the question that we posed at the beginning. Yes, for every natural number there is a group with order n, at least an abelian group. Later on we're going to see that for some numbers there are only abelian groups, like for example 17 or any prime number. We're going to show that the only possible groups with these orders are abelian. So we can say there is not always a non-abelian group for every number. Okay, well-defined means the following. There are many choices for this k here. For example, I could take 0 or in Z mod 5, Z, for example, I could take 1, but I could also take 6, and they would give me the same residue class. Same here. Now here I take 2 representatives, K and L, add them, and then take the residue class. So it might be possible that for different choices of representatives, this gives me a different result. And then, of course, this would be a senseless definition because it would depend on the choice of representative. If I chose 1 here, for example, and here the other representative, I would get a different sum, although these here are the same. This is not well defined, okay? So we have to show that no matter how I choose the representatives, this term here is always the same residue class. If you didn't catch that meaning, maybe now is another chance. So we assume we have 2 different representatives of the same residue class. K and K prime give me the same residue class, mod n, the same here with L and L prime. And now we have to show that for this choice of representatives, K plus L, residue class, is the same as for this choice, K prime plus L prime, bar is the same. Then this here is independent of the choice of representatives and thereby well defined. All right, so let's spell this out. So what does it mean for two residue classes to be the same? It means by definition that this here, k prime, is congruent k mod n. And this means exactly that k prime can be written as k plus some integer multiple of n. Because then and only then the difference k prime minus k is divisible by n. And of course then L prime can be written as L plus r times n for some integer r. So now we take a look at k prime plus L prime. This can be written as this plus this. And now this can be rearranged to give k plus L plus, here I can factor the n out. Okay, note to self, look up what ausklammern means in English. I just say factor out, that's probably not the correct term. And now this means, by definition of this modular arithmetic, here, this here is a multiple of n, thereby this difference here, this minus this, is divisible by n. This exactly means that this here is congruent to k plus L mod n. And now if I take residue classes, because those are equivalent or congruent, I have the same residue class. And this shows that this does not depend on the choice of representative. This is a very, very important concept when working with factor sets, and we will meet that again and again. So if you didn't get it first time, maybe the next time, but if you did, then it's a very good foundation for further work with factor sets. All right, so we know this is a well-defined operation. It is obviously an inner operation because I end up again with an element of z mod n. So zn or z mod n is closed under this operation. And now the verification of the three group axioms is really not that hard anymore, but a very, very good exercise, especially if you're a beginner. So the rest of this proof is left as a really doable but very nutritious exercise for you on problem set number 7. This is why we make this line in the proof box. Please really do that if you're a beginner to get a good grasp of how to work with these residue classes and why this here is actually an abelian group. And from now on, we will drop the circle and simply write plus. And it must be clear from the context that this is a new kind of plus. It is adding residue classes. We do not add natural numbers or integers, but residue classes. Here in the definition, we add integers, but then again, we take the residue class. Very important difference. Okay, to find even more example of finite groups, we now look at direct products of these just constructed integers modulo n. I didn't mention that before. Z1, which means z mod 1z or z mod z, is of course the trivial subgroup. If you understand that, of course, then you already have a good grasp of factor sets. If not, please pause the video and think about that. Why this here is not all of the integers, but actually the smallest possible group, namely the group consisting only of the equivalence class of 0. Please think about that. So let's try the first non-trivial example, Z2, which consists of two residue classes, the residue classes of 0 and 1. So in problem set, I want to say 3, 4, I think it was 4, I'm not sure. You showed that if you have two groups, you can easily construct or build their direct product, which again is a group, and it is abelian if and only if both of the factors are abelian. This is what we have here. So we take Z2 times Z2, which is just, as I said, the Cartesian product, meaning we take all the different two tuples of elements. There are only 4, because for the first one I have 2 choices, and for the second one independently I also can choose 2 elements here. So I end up with 4 elements of this Cartesian product. And as back then in this exercise, I defined the new group operation simply component-wise, meaning in the first component I add these residue classes, in the second component I add those. Now let's take a look at the group table. I abbreviate this here with E, but in abelian or additively written groups we often write 0 for the identity. So this is simply 0, not too confused with the actual integer 0. It's not the same, it's obviously a different 0, okay? But 0 bar would also be misleading. So I simply call it 0, and you have to have in mind this is not the 0 you know from the integers. So these here are called A, B, C. So as always, first row and column are trivial because the identity changes nothing. So here I have plus, and I do not write the plus in a circle, but simply you have to understand this is a new kind of plus. Now we add A with itself. A is this here. So in the first component we have 1 bar plus 1 bar, which is 2 bar, but the residue class of 2 is the same as the residue class of 0 because we are working modulo 2. So this here gives me the identity 0, 0, because in the second component obviously I still have 0 bar, 0 bar. If that was too fast for you, please write that down on your own. It's important that you understand the details, or let me do it for you. So by definition we add in both components, so here we end up with 2 bar, 1 plus 1 bar and 0 bar, but the residue class of 2 is the same as the residue class of 0, so I could write 0, 0 here, so this is 0. And the same for B in the second component, so I end up with 0 here, and also the same for C. Now isn't that interesting? 1 bar plus 1 bar is 0 bar, and the same in the second component. So all the elements satisfy that they are their own inverse, because now A plus A is 0 means exactly that A is the inverse of A. If you did the exercise with the classification of the groups up to order 4, you already know this group table. This was the second or the first? I'm not sure, I think the second group table. Now, what is B plus A? B plus A I have to add here and here, giving me 1 bar in the first component and 1 bar in the second, so this is C. And of course here A plus B is the same. This will obviously be a abelian group. Now the rest is clear because every element must appear exactly once in each row and each column. So here I have B, and also by symmetry here, and then here I must have A. All right, so this is the group table. This shows, this is no surprise, it's an abelian group and is one of the two groups of order 4. Please compare this with the table that we did back then. Maybe I'll show it to you. Einblenden in English, what does that mean? Have to look it up. So, and this here, this direct product, which is a group, is called V sub 4, the famous Klein 4 group. Felix Klein, famous German mathematician. Not sure in which context he came up with this group. Also called Vierergruppe. That's a German expression. I've seen this in the English literature as well. The Kleinsche Vierergruppe. Of course, Klein didn't become famous for inventing this here. He was a very, very famous differential geometry, for example, and maybe in studying transformation groups he came up with that, I'm not sure. And then to honor his life achievements, this was named after him, but this was not his important contribution to math. So now generally we write A squared, which is A composed with itself, but now in additively written groups we write A plus A as 2A, not A squared, but 2A. So this means in the Klein 4 group we have 2A equals 0, the identity for all elements. And a group fulfilling this is a so-called elementary abelian group. And one of the problem sets in one of the later exercises you actually proved that any group satisfying this must be abelian. Now comes the important observation. This here is a group of order 4, obviously abelian, and we already know from here that Z modulo 4Z is also an abelian group of order 4, but they are different. They actually correspond to both of the different group tables that we found back then. I also wrote down this notation below them. You see that here. So these are two different groups of order 4. So taking direct products actually gives us a new group here. It's the same with this direct product and Z mod 8Z. They are not the same group. Both have order 8, both are abelian, but they are different. They have different group tables. And later on we will show if groups are isomorphic, the order of the elements are the same. But here the so-called order is at most 2, because 2a is 0 for all elements. And here I have an element of order 4 or of order 8. More about that later. Running out of time and battery. And now what about this here? Is this maybe also a new group of order 6? Clearly it has 6 elements. So is this maybe different from that? This here you're supposed to study in the next problem set, and you will find, no, they are the same. The deeper reason for that will become later after we develop more theory. All right, that's it for lesson number 7. I promise, I hope I can keep this promise, the problem set will be not as long or complex as the last ones. And please do the exercises, and I will see you in the solution videos. Bye bye.